Hello everyone, here is homework number 30, simplifying rational expressions. We first define a rational expression to be basically of the form of a fraction, so ratio, rational, a fraction, of two polynomials. So we say p over q, where p and q are polynomials. And something important, of course, is that q cannot equal 0, because we would have division by 0. So here's some examples. Here's a simple rational fraction, just constants in both numerator and denominator. But then here's some examples of polynomials in both numerator and denominator. So any combination. And one of the things that we could do, as we've done in the past with many other types of functions, is to evaluate rational expressions by substitution, or sometimes people call this replacement. And so a few examples of this rational expression when y equals -2. So we just make our substitutions. Everywhere we see a y, we replace it by a -2. And remember, when you make the substitution, we suggest using parentheses around the value that you're substituting. In particular, y squared. If y is -2, it means -2 is a quantity in parentheses that's squared. Similarly, in the denominator, y cubed is -2 quantity cubed, and then plus 1. And then we just simply do the arithmetic. So -2 squared is +4. -2 cubed is -8. Don't forget to tag along the 1. And that gives us 4 over, combining -8 and 1, we get -7. And also recall that when we have a fraction with a negative in the denominator, it's preferred to associate the negative with the numerator. So instead of 4 over -7, we prefer -4 over 7. Or an equivalent form as well is the negative right out in front of the fraction bar. But this is more than likely the form that's most preferred. Okay, and then just one more example. Now x is a +2, so upon substitution, we're still going to suggest the parentheses, even though it might not make a major difference when you square it. But definitely when you have, so we have x squared, so 2 squared, and then plus 8, definitely in parentheses here, so it's understood that it's implied multiplication. And then don't forget to tag along the 2. And then similarly in the denominator, 2 squared -2 -6, and then do the arithmetic. So we get 4 plus 16 plus 2, or -2 -6. So that's 22 over, let's see here, we get 2 minus 6 is -4. We'll reduce that. 2 goes into 22 11 times, into 4 twice. And again, I'm going to choose to associate the negative with the numerator. Okay, so moving on. A little remark here. Since we have that our definition requires that q cannot equal 0, that is, the denominator cannot be 0, and that's of course because division by 0 is undefined. So to find where a rational expression is undefined, so this is often something we're interested in, we basically just find the values where the denominator is 0. So when you're asked to find the values where an expression is undefined, you just simply set the denominator to 0 So set the denominator equal to 0 and solve. And then that'll give us the values where x is undefined. Now some of these you could tell by inspection. For example, here we have 2x, so the only way this denominator can be 0 is if x is 0. But if we want to show it explicitly, we can state that this is undefined when the denominator 2x equals 0. And then we just simply solve that, so divide by 2, and so x equals 0. So that would be the value there, where that or rational function is undefined. Now in this rational function, the denominator is a constant. Notice that there is no variable. And so this is never going to be 0. So therefore it's defined everywhere, or for all, we should say defined for all values. In this case, we'll say of x, because the polynomial that's in the numerator is in terms of x. Okay, so then moving on, once again, just simply set the denominator to 0. Formally, we could say it's undefined when, and then we set the denominator to 0, and then solve the resulting equation. So that's a linear, or a little two-step process. If you want to show it explicitly, add 3 to both sides. We get 5x equals 3, and divide by 5. And so x equals 3/5 is what causes division by 0, which indicates that the rational function would be undefined. And then here we have a nice situation where, see, we don't pay attention to the numerator. It's not important for finding where it's undefined. It's only the denominator we're concerned about, because when that's 0, that's when it's undefined. So we don't worry about the numerator, and we just say it's undefined when, and then we set that denominator to 0. So in this case, x squared minus 5x minus 6 is 0. And we should recognize that, of course, as a quadratic because it's a squared, and it's a trinomial, so 3 terms. So more than likely came from the product of 2 binomials, set equal to 0. For the first term, we'll go with an x and an x. Okay, you could list, remember we do the factor method if you like. The factors is -6 because we want 2 numbers that multiply to give -6, that combine to give -5. And I think we got it right away, 1 and -6, right? You have to be careful though. -1 and 6, that would give you a +5. Then this one is a little tricky because 2 and -3, you're almost tempted to pick that, but that only adds or combines to -1. So -2 and 3. So that first pair we listed, 1 and -6, is correct. So x plus 1, x minus 6. And then recall we use the 0 factor property, so set each one of these equal to 0. So x plus 1 is 0, x minus 6 is 0. You can solve these mentally, but if you want to show it explicitly, subtract 1 from both sides, x is -1. Here add 6 to both sides, x is 6, and so therefore the solution, or the values of x that cause this rational function to be undefined, are -1 and 6. Typically my math lab asks you to separate them by a comma, as I did there. Okay, so one thing we want to do now is consider how do we simplify. So given an algebraic rational expression, how do we simplify? Well, let's go back to the concepts of simplifying numerical fractions. We say a fraction is in lowest terms or simplest form when numerator and denominator have no common factor other than 1. For example, 3 over 15 can be reduced. So that it's not in lowest terms, because there is a factor that is common to both numerator and denominator. Formally, we say we simplify the fractions by removing the factors of 1. So that's a formal way to go about reducing fractions. Some people don't like to use the term reduce, but that is what we do, is we divide the numerator and the denominator by their common factors. So an example of the two methods that are used, we'll show through this simple example here. Okay, we'll show removing common factors. Let me call this method 1. Roman numeral 1, and then dividing by the common factors, we'll call that Roman numeral method 2. Okay, so the way the textbook will show this is to write the numerator and the denominator, and this is typically not the way people go about it, but to write the numerator and the denominator as a product that contains the greatest common factor, where each product contains the greatest common factor between the two numbers. And between 15 and 20, 5 is the greatest common factor. So we write 5 times 3 to give 15, and 5 times 4 to give us 20. And then what we do is we remove the common factor of 5 over 5 to get 3/4. So that's typically the way the textbook will show it. But I think the way most people go about doing it is just think of dividing by the common factors. That is, if we start with 15 over 20 and we recognize that 5 is common, then we just divide the numerator by 5 and we divide the denominator by 5. And that gives us the same result, of course, because 15 divided by 5 is 3 and 20 divided by 5 is 4. Now, some people will even go through, let me label this as the cancel method, which I know is frowned upon by some instructors. But if you started with 15 over 20 and you recognize that 5 is common, some people won't even show this step. They'll just simply say 15 mentally. 5 divides into 15 3 times, and 5 divides into 24 times, so that gives us 3/4. So a variety of ways to go about it. Again, the canceling idea, some instructors don't like to say that word, but that's essentially the way most people will think about algebraic fractions, as we'll see in our examples here. Now you have to make sure you understand the concept of the binomial. You cannot cancel a sum or difference. You can only cancel a product. So x minus 7 is a quantity on its own, and so is this x minus 7. Okay, so the whole thing reduces. Let me write that again. X minus 7, again, is a quantity. It's a binomial, and so is this x minus 7. So people will think of maybe the fact that these reduce, we could remove those common factors and replace them by ones. Not many people will think of division, but you can. And I think most people actually think of cancellation. The fact that these are common, we'll just strike this out, replace it by a 1, and strike this out and replace it by a 1. So we get 1 over 1 or 1. Now, in this example, we actually have the same binomial. It's just disguised. That is, I'll leave the y plus 3 in the numerator, but by the commutative law of addition, I could reverse the order of 3 plus y and write it as y plus 3. And then we have the same situation as the previous example, where we can cancel the common factor. And there's no need to write 1 over 1. You could just simply go right to the 1. Now here's a special concept. The expressions a minus b and b minus a are what we call opposites. And the quotient, or the fraction, because quotient means division, so fraction, simplifies to -1 because they're opposites. Now here's the reason why. You don't need to show this every time. But if we start with a minus b over b minus a, and let's say we take both of these and we multiply the numerator and the denominator by a -1, because that's something we do in mathematics quite often, is multiply by an equivalent form of 1. So I'm choosing -1 over -1. Now I'm going to leave the -1 in the numerator. I'm just going to reverse the order and write this as -1 times the binomial quantity a minus b. But in the denominator, I'm going to distribute the -1. And when I multiply it by the b, I get a -b. And notice how I'm going to strategically place this here more so to the right, because when I distribute this -1 to the -a, I get a positive a. And so that gives me a minus b. And now the a minus b's in both numerator and denominator are common factors. So I could remove the common factors with 1, divide by the common factors, or think of it as canceling. And I think most people think of it as canceling. We replace those by 1s. We get -1 times 1 is -1 over 1, or -1. So we've shown that these reduce to -1. So what I'm going to suggest is this. When you identify opposites, because they're easy to identify, they're just in the opposite order in terms of being binomials, cancel one of the factors and replace it by a 1, and then cancel the other factor, the opposite factor, and replace it by a -1. So in this expression, okay, I'm going to rewrite it x minus 3 over 3 minus x. You don't have to go through this process every time, okay? This was just to justify it. And now we'll take the shortcut. If we recognize these as being opposites, binomials that are opposites, and again, it's easy to do so because they're just opposite signs. X is positive here, it's negative here. 3 is negative here, it's positive here. They're in the opposite order, so it's pretty easy to see. So once you recognize them as being opposites, you cancel one of them out and replace it by a 1. And typically we like to cancel the 1 in the denominator and replace it by the positive 1. And then we cancel the 1 in the numerator and replace it by a -1. And so that gives -1 over 1, which you really don't need to write. That's just -1. So similarly here, I'm not going to recopy it, I'm just going to work off the given. We should notice that the 5 minus x and the x minus 5 are opposites. And so therefore, we can cancel. And again, we're going to cancel the 1 in the denominator and replace it by a positive 1, and cancel the 1 in the numerator and replace it by a negative 1. And then we have the negative 1 in the numerator, and there's the leftover factor of x plus 3 in the denominator. So that's why we like to replace the denominator by the positive 1, because then it works out neatly when we have our simplified rational expression. So a general procedure that we're going to be using, and we'll go over these first few examples, and then we might cut the video short and have a second part. But the procedure we're going to be using is this. I mentioned we simplify them the same way we simplify fractions. But the first thing is to factor. So you got to factor the numerator and the denominator completely. And then divide out any common factors. And as I mentioned, it's the same as removing factors of 1. And I'm using the bad word cancel, right? Which some instructors don't like to hear you say. So remember, the first thing when factoring is to look for the greatest common factor. And for the numerator, so you keep the fraction bar. And in the numerator, between 7x and 35, a 7 is common. And if you have to get some scrap paper and go off to the side and work through the factorizations, that's fine. But 7 is common. And we'd open up a set of parentheses. Remember, we reverse the distributive property. And so we ask 7 times what is going to give us 7x, and that would be an x. And then 7 times what is going to give positive 35, and that's plus 5. And remember, there's going to be, when we factor out, the greatest common factor. So the greatest common factor here in the numerator was 7. And when we factor out the greatest common factor, we're going to have as many terms in parentheses as we had originally in that expression. In the denominator, the greatest common factor is x. So if we factor out an x and reverse the distributive property, okay, x times what gives x squared, that would be an x. And then we need x times something to give positive 5x, and that would be a plus 5. Okay, now I'm going to remove the arrows because they were just kind of used to help guide me in terms of my factorization. And this type of thing typically happens where upon your cancellations, you'll see something common. And now what we should recognize is that x plus 5 is common to both numerator and denominator. You can cancel them out. I always replace them by 1s. A lot of people don't even do that. They'll just cross them out and go right to the final answer in this case, which is 7 over x. Okay, so we have to be good at factoring. First thing to look for when factoring, as we saw in this example, is greatest common factor. Let's see what we have here. We have x minus 2. That's a binomial unique to itself. But x squared minus 4, we should recognize that as the difference between two perfect squares. So if you want to do this work aside, get scrap paper, x squared minus 4, remember the factorization of that, x and x, 2 and 2, one's negative, one's positive. So we express the denominator as x minus 2, x plus 2, Or vice versa, it could be x plus 2, x minus 2. But now we recognize that x minus 2 is a binomial quantity. So we'll put this guy in parentheses. And now x minus 2 is a binomial quantity is common to both numerator and denominator. You can think of dividing it out, removing the common factors of 1, or canceling. So just cross them out. You should replace them by 1s, because if you didn't replace it by 1, then you might question what's in the numerator. And in this case it's 1, and then we're left with the x plus 2 in the denominator. Okay, so we've got some more examples, but I think we'll call it quits for now. We'll do 2 parts to this video. So that's part 1, and we'll come back and see you for part 2 when you're ready.